Hello again, and welcome to the third lecture in the Sequences and series. That doesn't make a lot of sense. Welcome to the third lecture of this chapter, 10.3. Welcome to the lecture on section 10.3. So I'll get to full screen here and jump right into it. So far we've looked at a few special cases. So let's say chapter 10 so far. We can find a sum for we have sums for a geometric series, and that we determined was the sum equals the first term divided by 1 minus the common ratio. Okay, we also have, that was the first one we did. The second one was the telescoping series. And there's a number of those that we investigated. And there we found that the sum is simply the first term, because everything else goes away. So let's look at a more general we'll call it a positive series. So it's not, well, I'll describe what a positive series is in a bit. So we're not looking at any series, but we're looking at positive series. And answer two questions. One, does it converge? That's an important question. And two, maybe even more importantly, is what is the sum? So it's important to keep in mind that these are two separate questions. The second one relies on the first. Does it converge? We will try to answer that yes or no. And if so, what is the sum? These are the two questions we're going to look at today. Many of you might think, or you might rely inappropriately on a calculator. And so I'm going to extend that to say, what if we use a computer? And for an example of that, let's look at this harmonic series. The sum as n equals 1 to infinity of 1 over n. And just to help us out with the notation, that was 1 over 1 plus 1 over 2 plus 1 over 3 plus dot dot dot. It's possible that you might forget how to do all this stuff. When you sit down at the exam and you get this thing, well, does it converge? And you might find that you sit there and tap some things in your computer. You go tap 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 tap, and you do that a whole bunch of times, and then you could discover that s, that's a lowercase s, after 272,000 million terms. You type in 272 million terms of this series, and you'll find that it gets really close to 20. And you think, all right, so this has got to be good enough. The sum must be 20, right? Because I'm getting so close to 20. After 272 million terms, I've only got to 20. But a more ambitious student sitting next to you, who also forgot and is relying on their calculator pretty hard, might type in tap 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 this many terms, 10 to the, what does it come out to be, 43rd, and they might discover that, so this is, I don't know, billions of billions of billions of billions, that it comes really close to 100. So simply entering a bunch of terms in the computer and adding them all up and coming up with some number that looks like they must be converging is not good enough. And that is because in this particular case, 1 over n is not what we call bounded. So these things have to be bounded in order for them to be for the sum to exist. So let's take a look at a definition of bounded. We always like to have definitions to stick in here. Here it is. So here's a definition of bounded. A sequence, a sub n, is bounded from above. Bounded from above. If there exists a number m, big M, such that a sub n is less than big M, so each term is less than big M for all n. So the number m is an upper bound for a sub n. If m is an upper bound for a sub n, but no number less than m works, then we could say m is the least upper bound. So what does this mean again? So it doesn't matter how far out we go. We could go out an infinite 10 to the 43rd or 10 to the 103rd. As many terms as you can imagine, all the way to infinity, and a sub n will always be less than m. And if m is the least number that works for that, then m is the least upper bound. So, very related to this, a sequence is bounded from below if the same thing works, that little m is, all a sub n's are bigger than little m, no matter how far we go. So we're kind of trapped, either beneath big M or above little n. And if a sequence is bounded from above and below, the sequence is bounded. And if a sub n is not bounded, then we say it's unbounded. All right, so that's a lot of terminology. A question we might ask ourselves now is, does bounded imply convergence? Right? It makes sense. If we're stuck, it must converge. Well, what if I've got, let's say, the number -1 here, or let's call that +1, and I put a -1 down here, and so I say this is my big M, and then I go down here, and I'm going to say this is -1 is my little m. Well, what if my sequence goes like this? Or my series goes like this? Like, for instance, a sine wave or a cosine wave. Well, it's bounded, right? It's definitely bounded. It's stuck between big M, it's bounded from above, and it's bounded from below. But this will never converge on anything, because I just keep adding some positives, some negatives, some positives, some negatives. So it never really gets close, so this does not converge. Okay, so in order for something to converge, what else do we need for convergence? So let's take a look at one other definition here, and this is kind of a mathy sounding word, but it's important, and that's the definition of the word monotonic. A sequence a sub n is non-decreasing if a sub n is always less than n plus 1. That's another way of saying it's non-decreasing if the next term is always bigger than the one before it for all n. That is, a sub 1 is less than a sub 2 is less than a sub 3, blah, 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 blah. The sequence is non-increasing, right? That's the other way around, if a sub n is always greater than the next one. So the next term is always less than the first for all n. Now here's the important part of it, and let's make this red. What did I do for the definition last time? I made it yellow, I think. So it's monotonic if it is either non-decreasing or non-increasing. Now, the fact that they call this non-decrease instead of increasing, or non-increasing instead of decreasing, the reason they say that is because it just because it's non-decreasing doesn't mean that it's increasing. It might be holding steady, right? So it's not decreasing and it's not increasing. All right, so let's look at an example of that. What if we have some m, and my number m is up here, and I've got some sequence that is approaching from here, and it goes like this. And if these dots that I'm drawing in here represent my partial sums, so this is S sub 1, and this is S sub 2, and this is S sub 3, S sub 4, S sub n, and S sub n plus 1. Now let's think about this thing. If I am, say, monotonically increasing, or monotonically non-decreasing, which means I've got to be always going up or holding steady, and I'm bounded from above. I have to go up, I'm bounded from above, that means I'm going to converge. So let's take a look at a more formal definition of that and say this is, now here we've got a real theorem that says if a sequence A sub n is both bounded and monotonic, the sequence converges. My partial sums can't get above this, so I'm stuck. My sum has got to be right around here. And then there's a corollary to that. Corollary is another math kind of word that I'm not exactly sure what a corollary is, but we'll throw it in there anyway. This goes down here. Corollary to Theorem 6, it says that if the sum from 1 to infinity of a sub n of non-negative terms converges, if and only if its partial sums are bounded from above. So it's kind of saying the same thing, but a little different language. A series converges if and only if its partial sums are bounded from above. So that's kind of what I was trying to tell you with this thing here. It converges. So this has to happen. If they're non-negative, they've got to be bounded from above to converge. Let's look at an example of this. This might be a little bit more clear. I almost did that thing again. Let's erase that. Example. Is the series n equals 1 to infinity of 1 over n factorial? Is this bounded from above? Alright, well, let's write a few terms out. It's always a good place to start with that. That will be 1 plus 1 over 2 factorial, which is just 1 over 2, plus 1 over 3 factorial, which is 1 over 6, plus 1 over 4 factorial, which is 1 over 24. Where am I here? 24. Plus 1 over 5 factorial, this times 5, which is 120. So we're looking like that. Now, we don't know much about this, right? Because it's not one of these nice geometric series. It's not one of these nice telescoping series. So what can we do? Well, why don't we compare it to one that we know? So compare to, how about this one? 1 plus 1/2, and so far that's looking pretty similar, plus 1/4 plus 1/8 plus 1/16. All right, This one keeps going on forever. This one keeps going on forever. This one, however, we know this is geometric. So let's make a little parenthetical statement here. This is geometric. So this one, if I call this one, say, if I call this one A, and I call this one B, I know that A is always going to be less than B, or I could also say that 1 over n factorial is always less than 1 over 2 to the n minus 1, which represents this one here. So one is always less than the other. If B is bounded from above, then A is also bounded. Because I know that, the series I'm interested in, which is this factorial series, is always less than this one, right? And that's just convenient that it works out that this one is less than one that I know. Then this one certainly will be bounded. Bounded to what? I don't know. What is the sum? I don't know, but at least I know it's bounded. All right. Next page. Well, I don't have a sum for that one, at least I know that it's bounded. So let's look at another example. And things are starting to get a little clearer here, or they will shortly. What about the sum of n equals 1 to infinity of 1 over n squared? Is this bounded? So I could write out a few terms here. I could say that a sub 1 equals 1 over 1, a sub 2 equals 1 over 4, a sub 3 equals 1 over 9. They're definitely decreasing, but is the sum, or is the sequence of partial sums bounded? I don't know. Well, to make this example more clear, I'm going to think of the units on this as areas. So I'm going to say that each one of these A's is actually the area of a rectangle. And I'm going to say that the base of my rectangle is going to be 1, right? Which makes it real easy because then it's just 1 times 1 times 1. And then the height is my 1 over n squared. And you'll see why that is in a sec. So the height of my rectangles is always, the interesting number, and the base is just 1, so this thing becomes an area. Okay, but in my previous example, I made a clever comparison. This time, what can I use? Or here, let me write the question in nice proper English. To what shall I compare the sequence? To what shall I compare the sequence? Well, if I'm thinking about areas, and the reason I want to think about this in terms of area is that perhaps some integral will work. Perhaps. Put a question mark there. So I'm going to draw a picture, and I think I'm going to draw my picture. Yeah, I'll draw it here. This will work. So my one-axis will look like this, and my one-axis, if I knew how to use this better, I could make those perfectly straight lines, but I don't. And I know that, get out of there, that this function looks something like like this. You know, it's kind of decreasing in that sort of a way. This thing here is f of x equals 1 over x squared. And I could say that this is 1 here, this is 2, this is 3, this is 4. I'm going to go way out here and add an n, and this will be n plus 1. Okay. Now I could say that I'm going to draw in some different color here, some rectangles in red, because I'm trying to compare this to, if I go up like this, and then go over here, and then bring this back down here like that, and then this one will go over like this, and then this one will go over like this. Well, here I have some comparisons. So I could say that the area under this curve is somehow related to these sums that I'm interested in. So this is 1 over 1 squared, and then times 1. So this area is like this. So I've got the sum from n equals 1 to infinity of 1 over, what was it again, n squared. I can compare that to this integral, except by looking at this, I realize that my integral really is here. My integral from 1 to infinity of 1 over x squared dx. This area, this red area, these red rectangles, is really bigger than the area under the curve. Well, if I'm trying to prove this converges, then finding something that converges that's smaller than it doesn't really do me much good. So if I were to go out here, let's draw one more in red. I went out all the way out to n, and I drew that rectangle. Well, okay, so I've got something bigger. You know, I can perhaps prove that this integral converges, that the area under the black line, this improper integral converges, but it doesn't do me much good because it's bigger than what I'm trying to get. Alright, so I've got a clever idea. Let's do this one in green because this maybe will work better. I'm going to say, instead of looking at starting with 1, what if I started with 2? So I go up to here. Well, and this is the same rectangle if I just go over this way. It doesn't matter if I go to the left or the right. Starting with 1 over 2 squared, and then multiply that by 1, and then the same deal, I can go, the next one would be 3, the next one would be 4, and the corresponding one out here would actually be all the way out to n plus 1. So I've got a smaller rectangle that goes there. So really, over here I can take the sum from n equals 2 to infinity, and that's going to be, for sure, less than the sum, or the integral, which is really an infinite sum, of this function. Now, that becomes pretty useful because if I can prove that the integral converges, which is easy enough to do, we've done that in chapter 8, and that my integral is greater than the sum of these green rectangles, then I'm golden. Then I know that this sum converges. But you might ask, but I'm not interested in the sum from 2 to infinity. I'm interested in the sum from 1 to infinity. Well, if my sum from 2 to infinity converges, and I know what my first term is, well, then I'm done, right? Because it's the sum from, let me write this down, the sum from n equals 1 to infinity is really the same as a sub 1 plus the sum from n equals 2 to infinity of 1 over n squared. So if I can show that this converges, then I just have to add one finite number to it, and so that is still one finite number. A finite number plus a finite number is some finite number. So it's good enough for me to say that this converges. So it's good enough to compare this sum to this integral. All right, and now here's where we might take a look at a more formal definition again. That will be the integral test. Here we go. And that says, let a sub n be a sequence of positive terms. Suppose that a sub n equals f of n, which is kind of what I've got, 1 over x squared, 1 over n squared, where f is a continuous, positive, decreasing function. Those are all really important. It's got to be continuous, no jumps or holes or gaps or asymptotes. Positive, they've each got to be positive, so my terms are always getting bigger, my sums are always getting bigger. And decreasing, so that it's getting bigger by less and less every time. Function of x for all x is greater than n. Then the series and the integral both converge or both diverge. It's especially important to notice that it needs to be continuous over this. It needs to be continuous on the interval, and convenient that I've got that mark there, say 1 to infinity, or in this case n to infinity. Notice the square bracket. Oh man, this is a mistake here. My pressure-sensitive eraser again comes in. The square bracket around my left-hand side. That's very important because if my integral is improper both here and here, you know that my rectangle example would start to fall apart. So it's got to be continuous at my left end, and then it goes out to infinity, where I've got the round bracket there because that we can never really capture infinity. Okay, so let's use this to look at another example, and hopefully this starts to, hopefully the fog lifts a little bit and we can understand what's really going on. So the next example will be what we call the p-series. And the p-series looks like this. It's the sum from our old friend. This time I'm going to mix it up a little bit and use k. Right? I could use anything. K equals 1 to infinity of 1 over k to some power p. And what does that look like? That'll look like 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and that just keeps going on like that. All right. Now, some of you may have some ideas. So it's 1 over 1 squared plus 2 squared plus 3 squared. So if p was 2, but let's leave this here. So this will converge. Converge. If and only if, that's that if with the two f's, if and only if the limit as some c approaches infinity, right? This is my improper integral here, of the integral from 1 to c of x, and now instead of writing this 1 over x to the p, I'm going to write x to the negative p dx exists. So this integral has to converge in order for this series to converge. So how do we find this limit? Well, let's just evaluate the integral. Power rule, this is a pretty easy one. Increase the power by 1, so a negative p goes to negative p plus 1. I prefer to write that as limit as c goes to infinity of power goes up by 1, so it becomes x to the 1 minus p over divide by the new power, which is 1 minus p. Now, this will obviously not work when p equals 1. Works only when p is not equal to 1. So, let's say p is greater than 1, it will converge. When p is greater than 1. Why is that? Because when p is greater than 1, the exponent becomes negative. And since I'm going from 1 to infinity, if p is greater than 1, the exponent is negative, which means it's really on the bottom of a fraction, which means that when I stick in infinity, that'll go to 0. When I stick in a 1 for x, remember I'm not sticking a 1 in for p, I'm sticking a 1 in for x, 1 to whatever will just become 1. 1 minus p will, as long as my p is positive, it'll become some negative number, subtracting a negative number. This will make more sense when I do an example. So it converges when p is greater than 1, and when p equals 1, it really just becomes a natural log, which then also diverges. So we need p to be greater than 1. Let's just do an example to make more sense. So here's an example. The question is, does this series converge? Well, we know that converges if the integral converges, which we know the integral becomes x, and I'm just taking this from down here rather than going through the integral, 1 minus p, well, 1 minus 1.0002 will become negative 0.0002 over 1 minus p, which is negative 0.0002 as I go from 1 to infinity. Well, this is, when I plug the infinity in here, well, let's rewrite this. This is, it's a little more clear, and that's what I tried to explain before. 1 over, I'm going to take that negative sign and move it up to the top, 0.0002 times x to the 0.0002. And I'm going to evaluate that from 1 to infinity. Well, when I stick an infinity in here, that becomes 0, right? Minus a negative, when I stick a 1 in there, it's just minus negative 1 over 0.0002, because this just goes to 1, which is, I think, 5,000, equals a positive 5,000. So that's interesting that when we have a power that is very close to 1, we know that it doesn't converge at 1. But when it's very close to 1, but just a little bit above 1, it still converges, but man, it adds up to a pretty big number. So that works out. And hopefully that cleared up what I was trying to explain over here, which just didn't go too well. What about another example? Let's try. Does the sum from n equals 1 to infinity of 1 over the square root of n, does this converge? Well, same deal applies here. We can check it out. That equals the sum n equals 1 to infinity 1 over n to the 1/2. Well, 1/2 is less than 1, so I suspect this won't converge either. So at this point I can skip straight to the punchline and say diverges by the p-test. Okay. Now let's look at one that's a little trickier. How about does the sum n equals 2 to infinity? I'm going to make sure this is a separate. N equals 2 to infinity of 1 over n times the natural log of n. Does that converge? All right. Well, this one doesn't. This one's not as obvious as the p-test. Right? There's no particular power down there. It seems like n is greater than 1, but it's not really n times n. It's n times the natural log of n. So, gut level feeling maybe it converges because we're dividing by something bigger than n, but we don't know. Let's take a look. Here we have to do the integral. So I'll take the integral, and again I'm going to use some sloppy notation. From 2 this time, from 2 to infinity. Now why am I using 2? Why would I not start at 1? What happens if we stick a 1 in there? Think about that. You might have to pause. Think about what happens if we put a 1 in there and a 1 there. I'm going to rewrite this as 1 over the natural log of x times 1 over x dx. Right? Well, I could say, I do a little u substitution here. I'm going to say that u equals the natural log of x, which means that du, the derivative of natural log, is 1 over x dx. Now that's convenient because here's 1 over x dx, here's 1 over u, so this becomes the integral of 1 over u du, which I know equals the natural log of u, which will equal the, and notice I didn't put limits of integration in here because these limits 2 and infinity are x, they're not u. So now I'm going to back substitute, put this back in here. This becomes the natural log of what was my original, oh, it was natural log, so it's the natural log of the natural log of x. And I'm going to evaluate that now, because now I'm dealing in x's. I can evaluate that from 2 to infinity. Well, the natural log of infinity, well, that just goes off to infinity. The natural log of infinity goes to infinity. So this really becomes infinity minus something natural log of 2, which is whatever, natural log of 2, which is some constant number, but it doesn't matter. So this diverges. That one diverges. All right, well, let's, and notice, I just want to point out here that because someone watching this that's not from Madison College is going to harp on me that I stuck infinity in here. Technically, I should write this as a limit of something, you know, as it approaches b, limit as b approaches infinity of 2 to b, something like that. But realize that this is somewhat sloppy notation, so please don't send me any hate emails or make some comments on the YouTube. I realize that I'm doing that. Let's do one more. And this will be the last one, and we're going to... remember, one of our questions is, does it converge? The other question is, what is the sum? So let's look at a final example for the day. And that final example is the sum from n equals 1 and you guessed it, to infinity of n over e to the n squared. Well, the question is, does it converge? And if so, what is the sum? So let's do the integral test. So I'm going to take the integral of x over e to the x squared. I'm going from 1 to infinity times dx. I'm going to rewrite this in a way that looks a little more familiar to us, and that will be as the integral from e to the negative x squared times x dx. Alright, so now I look at this, and this to me says u substitution, right? And I'm going to go through this quickly, and if you're still struggling, take some time to do this. So du then equals negative 2x dx. Right? But the problem is I don't have a negative 2x. So what do? I take my technique, I just put a negative 2 in there. But if I do that, I've got to put a negative 1/2 out here. So this thing becomes my integral negative 1/2 of e to the u du, which equals negative 1/2 e to the u, and when I back substitute, it's negative 1/2 e to the negative x squared, evaluated from 1 to infinity. Okay, well, if I do that, that becomes negative 1/2. E to the negative infinity is 1 over e to the infinity squared. Well, we're pretty sure that's 0. Minus, stick a 1 in there, e to the 1 is, e to the negative 1 is just 1 over e. So I have negative 1/2 times negative e, negative 1 over e, and that equals positive 1 over 2e. Okay, so here I just paused for a moment, and if you look over to this side here, I did 1 over 2e, and that is, I better make this an approximately, this is exactly equal to 1 over 2e, which is roughly equal to 0.18394. Okay, so let's go back to full screen here. So my question is, does it converge? And my answer is yes, this converges. So once again, let's say we're taking an exam, and a problem like this comes up on the exam, and I say estimate the sum, and you forget how to do this. Okay, so you're going to estimate this by just punching in your calculator. So you get 1 over e to the first plus 2 over e, well, that'd be squared to the fourth, plus 3 over e, that would be to the ninth, plus 4 over e to the 16th. Now e to the 16th is getting pretty small, but you're going to be really accurate and say it's 5 over e to the 25th. And you discover that that equals 0.4048814. Well, what if you try that again, just to be sure, and you say it's 1 over e to the first plus dot 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 plus 7, so we're going to the 7th term, e to the 49th, and what is that going to equal? Well, that equals 0.40488814. Well, now, obviously, when I punched this into my calculator, I had some rounding here or there. So maybe I should investigate what is my error. So I'm going to define this thing called a remainder. And I'm going to say that the remainder sub n is my actual sum. And I don't know my actual sum yet, because I only went up to the 7th term, or the 5th term, minus whatever my partial sum is. And that's my remainder. And that equals that will equal a sub n plus 1 plus a sub n plus 2 plus dot 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 dot, right? So whatever I came up with, which is only up to 5 or up to 7, you know, whatever's left must be my remainder. So here's a good opportunity to give your last formal definition of the day, and I know this one is getting long. The remainder. Bounds for the remainder in the integral test. Suppose that a sub k is a sequence of positive terms, a sub k is f of k, blah, 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 blah. This is the same stuff we've been doing. Then the remainder, r sub n, s minus s sub n, is this, is going to be stuck between n plus 1 to infinity and n to infinity. So let's think about why is that. Why is our remainder going to be greater than the n plus 1, but it's going to be less than the n? Well, let's go way back to this picture, which I'm not sure what page it was on. We got to go so far back. Here we go. So the remainder is going to be, remember that this n plus 1 thing, I really shifted it over to get some green rectangles that are less than the integral. And so the green represented n plus 1. In this case, it was 2. The red represented, you know, something that was greater than the actual integral. So that would be the n. So my n, if I start at my n, it gives me something bigger. If I start at n plus 1, it gives me something smaller. So it makes sense then that my remainder will be in between the smaller estimate and the bigger estimate. So if I stick that in there, my remainder is going to be somewhere between the integral of 6 to infinity, say if I'm for my 5th term, so I'm going to say r sub 5. My remainder will be somewhere between x over e to the x squared dx. That's going to be, my remainder is going to be pinched in there somewhere between which one, the integral from e to the 5 x over e to the x squared dx. So when I plug these actually in here, this becomes 1 over 2e to the 36th. My remainder is going to be between that and 1 over 2e to the 25th. Okay? And to put a sense of scale on this, this becomes 1.16 times 10 to the negative 16th. Right, we're looking at a pretty small number there. My remainder is going to be between there and 6.94 times 10 to the negative 12th. So my remainder is in a very, very narrow range of small numbers, very, very small numbers. So really going out to the 5th term, the 7th term, gave me a pretty accurate range of what my final sum is. But speaking of my final sum, why did I bother with this? Why bother? Don't I know the sum already? Or in other words, does the sum from n equals 1 to infinity of n over e to the n squared, does this equal the integral from 1 to infinity of x over e to the x squared dx? Does this thing equal? Well, here I came up with my sum of the first 5 terms is 0.404. Here I came up with the first 7 terms, 0.404. But when I did it earlier, and I did this integral, it converged on some value 0.183. Now, does that make any sense? Well, remember, when I did this picture way back here, my integral is actually the area under this black curve. The sum I was after was really these red rectangles here. They're clearly not the same, but I'm not after the area under the curve. I'm after this sum represented by the red rectangles. They are not the same. The integral test only allows me to determine if it converges. It does not give me a final sum. So the answer here is a very resounding, I'm going to go big, no. No. This does not equal. Okay? Somebody will make this mistake, and I will not give you any credit, because this is an integral test, not an integral method to get that sum. So I hate to leave on a negative note, but this is a very important thing to understand, and we can talk about this more during class. With that, I'll say thank you, enjoy the homework, and I'll see you soon.